Yeah, ladies and gentlemen, I would like to give you a presentation on the service life for concrete structures for 100 years and more, and the tool which we use to verify this very long service life. Concrete is our most universal and robust construction material which we have on Earth, and has therefore obtained a dominating position in construction. We have designed very spectacular infrastructure projects. Here the last one is a composite bridge in Lucerne. Unfortunately, we also see this kind of structure. A heavily corroding crash barrier at a Danish motorway, a deck and a column after, say, 20 years of exposure to the icing salt. Similar happens also in this part of the world, very close where we are. Have a look. This is a pier very close to the Golden Gate Bridge. You might know it. Also here, very heavily corroding crash barriers. The deterioration of concrete structures, or the service life of concrete structure, requires an understanding of the deterioration which is ongoing. Aging and degeneration is a natural and unavoidable process of all construction materials. It is not the question that they degenerate, but the question is at what rate. For concrete structures, we have normally three typical mechanisms. The electrochemical ones, the rebar corrosion, back once again. We have chemical ones, alkali silica reaction, sulfur attack, delayed attringite formation, and physical ones. I believe you will go into this a little bit more later on. Nowadays, our clients require service life of about 100, 120, and even 120 years. Let us see what our traditional codes say, quote, with regard to the concrete and the durability. I had a look in your ESTU standards, and I found very few remarks on concrete durability. They are very general, as quoted here. It is to recognize that the significance of corrosion and deterioration. This is very few lines what we expect in the standards. We can conclude that there is some expectation for durability in your ESTU standard, but all recommendation are qualified as deemed to satisfy requirements. And the standard gives no guidance on how long a structure should remain in service. It lacks of prediction models, and there is no test method to verify the service life of a concrete structure. And this accounts not only for your code and standard, this accounts also, or has account for a lot of European standards. This means, and we should be aware of that all codes normally require the minimum quality. The knowledge of the codes is often based on a knowledge which is 10 or sometimes even more than 30 years old. The durability of concrete structure is introduced by substitute deemed to satisfy requirements. And the service life is assumed in the standards are normally only 50 years. But today, our clients demand more. So this means our traditional codes and standards are not adequate anymore as service life design basis. We need new durability approaches. And what would we expect as a new durability approach? At least these different items. We have to establish the service life, we have to identify the environmental exposure, we have to identify the decisive deterioration mechanism. We have to establish some mathematical modeling to calculate the deterioration, and we have to set some damage limits, acceptance criteria. The awareness that our traditional codes are insufficient has been known since the 90s, during the last centuries, at least in Europe. And therefore we developed in Europe, within a European research project, which we called DuoGrid here, in the late 90s, a new durability design tool. It's actually a probabilistic-based, performance-based design tool for concrete structures. 12 European partners were involved, starting from the industry to the research institute, contractors, and even clients and owners were involved. And this new tool, which has been developed within this European research project, is called commonly DuoGrid. Kobi was the scientific manager of this DuoGrid project. This new durability tool is now implemented in the new FRB model code for service life since 2006. It has heavily been used in Europe, and in addition it will be implemented in the new FIB model code, which has been presented in Washington this year. This is the flow chart to make a durability design in accordance with this FIB bulletin 44. We have 4 levels of durability design. To the left we have a full probabilistic approach, and to the right the avoidance of deterioration approach. I will concentrate on these both approaches here in the following presentation. Here again there's 2 approaches. To the left, the full probabilistic approach. Within this full probabilistic approach, which accounts for carbonation and chloride-induced corrosion, the deterioration will be modeled. And this modeling is the key tool to make a true service life design. You might know all this service life which we have for concrete structure here. Normally we have an initiation and a propagation phase. And within the purpose of this full probabilistic approaches, we find the optimal design. This means the optimal cover or the minimum cover, and the optimal material to resist the deterioration at least a certain period of time. In contrast to that, the strategy B says you have to avoid the deterioration right from the beginning. We can use non-reactive aggregate, sulfate-resistant cement, we can use steel fiber reinforcement, stainless steel, cathodic prevention, protection. I will show a little bit more the full probabilistic approach. Here the different step of the full probabilistic approach, which I will call in the following DuoGrid, but it's nowadays similar to the FRB model code. I said there are different steps, and the first step is to define or to select the decisive deterioration. Is it chloride-induced corrosion, or is it carbon-induced corrosion, or what else? Then we have to define the limit state. The client has to say, what determines the end of the service life? Is it the corrosion start? Is it the cracking of the concrete, or the spalling of the concrete? Then we have to define an acceptance criteria. This means the probability of having corrosion after 100 years or 200 years. And as it is a probabilistic approach, all parameters have to be quantified in a statistic way. I will show this further. Here the first step, the selection of the limit state. The limit state means the end of service life. And for chloride-induced corrosion, the end of service life is normally the period when corrosion starts. In our case, we define the limit state when the critical threshold limit will be achieved at reinforcement. And this critical chloride threshold level depends on a lot of influence as parameters, as you can see here in this illustration to the right. The next step is the modeling of the deterioration. In that case, we use a model which is based on Fick-Seccond's law, which is a very well-known model for chloride ingress, but modified by a chloride migration coefficient here, D, and by an H factor, because we know that the concrete becomes denser and denser with time. This means the chloride migration coefficient decreases with time. And this is the famous H factor here on top. The next thing is to put in the input parameters, and as a probabilistic approach, all input parameters have to be defined by a minimum value, by a standard deviation, and a distribution function. And here again, the chloride migration coefficient, for example, a value here, which is a reasonable value for Portland cement and fly ash cement. And this chloride migration coefficient is one of the key durability parameter which the contractor has to comply with. It's similar to the compressive strange. If we make a structural design, we specify a compressive strange class, for example C40. And the contractor has to produce a concrete with this compressive strange. And he has to make a lot of testing during pre-testing and production testing. And the similar is that we require now for this chloride migration coefficient. It is a functional requirement in our concrete specification. And the contractor has to comply with that during pre-testing, full-scale testing, and production testing. It's a very, very new approach, but I must say our contractors in Europe have adopted this approach since the last 5-10 years.
So they measure the diffusion coefficient instead of doing column tests?
Yes, and I will come back to this again. Yes, this is very, very interesting. This is the next step is this is the result of such a probabilistic calculation. It's showing the probability of corrosion, that corrosion starts in relation to the service life of a structure. And in that case, after 100 years, we have a probability of 0.02. This means 2%. In COVI, we have used this Duracrete or FRB model since the last 10-12 years at all our larger infrastructure projects, tunnels, bridges, and marine construction, especially if they are exposed in an aggressive environment. This tool allows us now, as a consultant, designer, to calculate the minimum cover and the maximum chloride diffusion migration coefficient to ensure a service life of 100 years, 150, or whatsoever. I will show some examples. The first example where we used the approach in COVI is in South Korea. It's the Busan-Gyeorghe fixed link, which combines the city of Busan, Korea's second largest city here, and the island of Gyeorghe. The reason for the link was to shorten the distance between these two cities. The link consists of an immersed tunnel, which is here. You can see it here. It's the deepest immersed tunnel in the world with 50-meter water pressure, which gives high demand on the water tightness of the joints and so on, and 2 cable stayed bridges here. The client acquired 100 years of service life. according to the design basis, the contractor